SwayamPrabha. Digital India. Educated India.
So students, now in the last part of this course, I am going to talk something different, something which is to do with ceramics. So it is known as transformation toughening. So it has two words, transformation and toughening. Basically something which is related to toughening, but it is introduced by transformation or rather induced by transformation. So or phase transformation by the way. So before actually I discuss, we will first give you some insight about ceramics. So objective of the lecture is basically to show you how to exploit the microstructure basically to maximize the toughness of a material. Some of these lectures are materials of the lectures are taken from the Carnegie Mellon University, and I would like to acknowledge that, but some are basically from the books. Well, ceramics are traditionally brittle materials as compared to metals, and that means they have very low toughness. So purpose of the microstructural engineering is to increase the toughness, and I will first discuss what is ceramic, why structural ceramics are important, and then I will talk about something about why toughness is important, what are the ways of increasing toughness, and finally we will discuss about the transformation toughening. So first let me give an example. Okay, ceramics are also used as a structural materials like aluminum oxide Al2O3, zirconium oxide ZrO2. They are the two workhorse of ceramics which are used extensively in many structural applications. Cutting tools, they use also aluminum oxide, but they also use tungsten carbides. So structurally ceramics are used, but another important niche application of ceramics is gas turbine engines. We know gas turbine engines are basically consisting of nickel based superalloys with a coating of some zirconium oxides to protect them from the oxidation and also the thermal issues. But the efficiency of any kind of a turbine engine, as you know, is related to the temperature to which we can reach achieve during our operation. So the barrier or the basic problem of reaching high temperature is limited by the melting temperature of the material. So nickel based superalloys cannot be used temperatures more than 700 degrees Celsius temperatures, okay, and that is why there is alternative search of new materials, and ceramics obviously have much higher melting temperature, so they can be used. But the problem is that ceramics are relatively brittle, they have very low toughness. So therefore toughening of the structural ceramics is essential if you want to use them as a material. Silicon nitride base, suppose shown, this is silicon nitride base taken, this is taken from US websites, remember, they actually can be used up to a strength of 960 MPa and at a temperature of more than 1200 degrees Celsius. So there are use of these kind of gas turbine blades. These are the gas turbine compound, and this is the main turbine blades of silicon nitride. Okay, so before I go into strategies of microstructure, let me just give an example, issues of ceramics. Structural ceramics, which are oxide ceramics, there are basically several ones. Most important one I told you, aluminum oxides Al2O3, which is used in many applications. Cutting tool is one of those. There are many others, porcelain, zirconium oxide or ZrO2, which is also known as zirconia, and most importantly which is used extensively used is a partially stable zirconia, which will be our main topics of discussion later on. So I will not discuss now. It can be it can contain many other oxides, but this is stabilized zirconium. Then other than that, you also have mullite, spinel. Mullite is aluminum silicate, spinel is magnesium aluminate, or you can have sialons, or you can have coderites, which is nothing but a magnesium aluminum silicates, or you can have aluminum titanate also. But mostly these are the oxide ceramics. There are other things like silicon nitrides or carbides. So, structurally the ceramics are also extensively used. Let me just give you some idea. These are the nitrides and carbides. If you see here, there are many things. There is silicon carbide, boron carbide, titanium carbide, silicon nitride, and boron nitride, cubic boron nitride, one of the hardest materials available other than diamond. So, they are also used in various structural applications. Zirconium oxide, which we will be discussing a lot, has is a many interesting applications like piston bulbs, sealing bulbs, or even you can also use many other applications like dye material in a metal industry, thermal barrier coatings. Just now I told about nickel superalloys, or cutting tools. So, normally these are stabilized, and I will discuss what is stabilized meaning, because that requires discussion of phase diagrams. Remember, it can be stabilized by yttrium oxide or calcium oxide or magnesium oxide, very low amount, 3 to 10 percentage. Melting temperatures are very high, about 2500 degrees Celsius temperatures, which is very rarely can be achieved. You can achieve in metals. Normally these ceramics are sintered, so therefore they will be we will start with powder, and powders are sintered to make a components. Sintering temperatures are quite high, about 1800. More notably, the fracture toughness can be tuned from 6 to 20 MPa root meter. That is extensively high. Normally silicon carbides or other things, even aluminum oxide has a fracture toughness of close to 2.5 MPa root meter. Compared to that, this is just like 1 order of magnitude higher. 20 is 10 times 2. So, and this has a yield strength of bend strength about 400 to 700 MPa, and modulus about 107 to 210 GPa. This is our classical materials, which classical zirconia, which is used in many structural applications. Now, as I told you, okay, let me also tell you that zirconium oxide can be, this is a polymorph. It has many polymorphs. It can exist in 3 different forms. That is why the interesting things comes into picture. First one is a cubic zirconium oxide, which is also known as C phase, because cubic, it is stable at very high temperatures from 2370 to 2680 degrees Celsius temperature. Then they also has a tetragonal phase, which is known as T phase, with the C by A ratio is close to 1.02, very small ratio, but it is tetragonal, by the way, and it has stability range a little lower from 1240 to 2370, and at low temperatures, that is less than 1240, zirconium oxide, pure zirconium oxide exists in monoclinic form, which is known as M phase, actually not C phase, M. Okay. Now, cubic phase, which is stable at high temperature, as you see beyond 2370 degrees Celsius temperature, can be stabilized by using dopants like calcium oxide, magnesium oxide, yttrium oxide. Tetragonal monoclinic phase transformations, this transformation from tetragonal to monoclinic involves volume increase of 4.7%. That is the basically important thing which you must remember, and this volume increase is what is the basis for transformation toughening. Okay. So, I will go back, get back to you about these aspects little later. Let me just go back now, okay, because we need to discuss some things interesting. As I told you, ceramics are traditionally brittle and they have very low toughness. So, obviously that means we must develop strategies to increase the toughness of ceramics. But what are the strategies? Obviously one of the strategies is microstructural engineering, as I told you. Yield strength, we know that it depends on obstacles to dislocation motion, okay, or even if you can understand the even the strain hardening coefficient in a stress strain curve, it also depends on how dislocation actually acts as an obstacle to the other dislocations or even some other defect structure. But toughness is very complex. Now, there is no direct correlation, okay, that it is if I increase dislocation density, decrease or whatever, it will affect. So, that means toughness has to do with something else. In fact, toughness has to do with the crack. As you know, the cracks exist in every material. Okay, only thing varies is the size of the cracks and the number density of the cracks. If you just throw a stone into a windshield of a car or even a window glass, it breaks, okay, because the cracks which are existing in the material, which is called pre-existing cracks, they propagate and the sizes are quite big, number density is quite high, that is why. But if you simply take a metal, piece of metal, and if you heat it hard, it will not break. That is because metals can absorb energy, they can plastically deform, first of all important thing. And second thing is that the crack whichever exists in the material has a size much less than the critical size required for it to propagate. So, that is why metals are always tough, they can absorb deformation, they can energy, and they can can be used for various applications which requires impact loading, but ceramics are not, but that is not always true. So, therefore, if you want to increase the toughness, we must look for ways and means to eliminate or minimize the cracks. In fact, elimination of cracks completely is something which is ideal situation, is impossible in the world. What we can do is minimize the cracks, or other way is ways and means to maximize the energy cost for propagation of the cracks. As I said, that is very difficult to eliminate cracks. So, obviously one can actually engineer the material or microstructure in such a way that the energy required to move a crack or propagate a crack is very high. There are many ways of doing that, I will show you that. So, that is the very important thing. Now, how to minimize or eliminate cracks? Remember, I just put eliminate underline because elimination is extremely difficult or in many cases impossible. First consider what are the sources of cracks. In the metals there will be voids, like if you do solidification you can have deleterious effects like pores, because there will be gases, many other reasons for the pore formation solidifications. Okay, or you can have also surfaces which is rough. Why? Because your machining can lead to rough surfaces, so that rough surfaces can trigger the crack. Also in metals you can have poorly bonded second phase particles. Okay, suppose you have a dispersion strengthened alloy, you have added something, if you add oxide dispersed nickel or oxide dispersed steels, these are available in actual applications, then the bonding between this oxide and the steel or oxide and the nickel may not be perfect or may not be good, actually not perfect, good. So, basically because there are ceramic and metals may not have a compatibility as far as bonding, as far as thermal expansion is a concern. So, therefore, there is a chance of void nucleations. So, therefore, removal of these interstitials, which is very common in steels. Okay, those who work on the steel, we know that steel making is an oxidation process. You are burning a carbon rich material, carbon, phosphorus, sulfur rich material using oxygen, and the control of oxygen plays the important role, but in actual sense it is not possible to control the oxygen concentrations which you are putting inside a converter during steel making process perfectly. So, there will be always some dissolved oxygen, not undissolved, dissolved oxygen in the steel before it is to be cast. So, these oxygens are dangerous because why? Because first of all it will react later on with the steel, and also it can create blowhole, porosity, many other defects. So, the oxygen is to be removed. So, one of the removed oxygen is to add into it some deoxidants which will react with the oxygen and take care, but they will produce oxides. One of such is aluminum. Aluminum is just used to take care of the oxygen which is dissolved in the steel, and so it reacts with the dissolved oxygen and form aluminum oxides, and these oxides can remain trapped inside the steel and that can create cracks. So, therefore, in one of the ways of eliminating is to remove the oxygen, carbon, nitrogen, sulfur from the steel, but it is because they produce brittle inclusions. So, these are the different sources of the cracks in the metals, but there are others, I am not taking you exhaustively its list. Okay. So, how to minimize them? There are various mechanisms which can lead to cracks at the gain boundaries, grain boundary actually sources of defects or tipple junction points. Therefore, in some materials, especially metals and now ceramics also, making the grain size is one of the means of increasing the toughness. Why? Because smaller the grain size, smaller is the crack size. Bigger the grain size, probability of making the crack is big, making the crack bigger is high. So therefore, crack size matters. Why? Because as you know, I cannot give you a complete lecture of how the cracks actually propagates. The Griffith's theory of cracks, nucleation and crack propagation tells you the stress required to move a crack, it depends on the crack's size. The half of the length of the crack size dictates the stress required to propagate a crack. So therefore, if I make the crack size smaller, the stress required will be higher. So therefore, the toughness will increase. So that's why all the nanocrystalline materials, whether it's a ceramic or a metallic, will have better toughness, higher toughness than the microcrystalline grain size. How to minimize the grain size? There are many ways. You can do the thermomechanical treatments, like you can just simply deform it and then you can do recrystallizations, or you can actually start with a powder with the nanocrystalline grains. Like nowadays, we can actually ball mill the powders, produce a nanocrystalline powders and then sinter it using a better advanced sintering techniques to produce 100% density, so that there is no cracks or the pores or something, and grain size also remains smaller. So this is one way of doing that. Other way is many other options. You can absorb the energy, okay, because anyway when you cannot stop remove the cracks completely, it's impossible. So cracks will be present in the material. So you can actually make the crack to move difficult or movements difficult. How it increase the amount of energy consumed when it's a cracks propagate. Okay, so normally what happens when a crack propagates the material, the region near the crack tip will be plastically deformed. So there will be some, whether it's a ceramic or metal, it will vary depending on the type of metal, type of material, whether it's a plastic or non-plastic, deformable or not, but there will be some micro plastic deformations even in ceramics with the crack at the crack tip. So that means what? We can actually maximize the amount of the plastic work. How? Very simple. Work done in a material when you are deforming it, it is basically nothing but the area under the stress strain curve. If this is the stress strain curve of a ceramic, this is stress strain curve of metal, basically work done by is nothing but the area under the curve. So if I increase the yield strength very high, area under the curve will automatically increase, okay. So if we decrease the yield strength, what we can do? We can actually basically maximize the size of the plastic zone. Why? Because the yield strength is at the boundary between the elastic and the plastic deformations. As the yield strength decreases, the plastic deformation can start at lower stress. So that's why actually you can increase the plastic zone by this way. Other way of making the material tough is what exactly I was telling. You can actually increase the yield strength little high, much higher, so that the area under the curve also increases. It can absorb more energy. For very tough materials, it turns out there are some same parameters that control ductility also affect toughness. That's what exactly. The lower density of the second phase particle increases toughness. Lower density means the density of rho. Second phase particle well bonded to the matrix increases also toughness. That's what we know in case of precipitation hardened alloy. The atomic resistivity between the precipitate and the matrix, that's what controls the strength and the toughness. Small difference in thermal coefficient expansion coefficient sometimes helps. Why? Because it will lead to stress between the particle and the matrix, because as the thermal expansion coefficient different, when you heat it up, the particle may expand more than the matrix or expand less than the matrix. This will lead to stress, thermal stress, and that thermal stress actually helps in creating toughness. Second one is that other things are called extrinsic, these are intrinsic. There are three ways of doing that. One is known as the crack deflection, or what is known as meandering of cracks. Those of you who have seen the rivers, they just meander through the plains. So same thing can be done. The cracks can be asked to meander through the material. Or you can do zone shielding or contract shieldings. Shielding means what? Shielding means the tip is shielded from some part of the applied stress. Okay. See, remember, if I give an example, if I have a crack in the material like this, and if I want to make the material break, what I should do? I should make the material, make the crack propagate to the material. Okay, that is what I should do, then it will break completely. So, one way of that means what? The crack has to be open up. So, if you apply stress like that, tensile, the crack is exactly open up or this opens and then it spreads to the material. So, in general, shielding means the crack tip, which is basically going to open up and move, is shielded by the applied stress. That can be done by creating a compressive stress layer around the crack tip. If you have a compressive stress layer here at the crack tip, even if you apply tensile stress, this compressive stress will not allow the crack tip to propagate faster. Okay, because first the compressive stress field has to be overcome by the tensile, applied tensile stress, and then only it can reach the critical stress required to move this crack. So, that is basically possible only when the sufficiently higher tensile stress applied. So, therefore, by creating such a kind of a shielding, we can actually what is known as zone shielding. Discussion was mostly on metal base, but which are interestingly tough, and steels are interestingly tough because they can absorb plastically, the crack tip is plastically deformed, or this kind of compressive stress layer can be created, or you can actually allow the cracks to meander through. All these things are possible in a metal, but these are except obviously at low temperature where BCC metals are also brittle. But intrinsic toughness method is mostly concerned ceramics, because intrinsic toughness of ceramics are very low. So, there are different types. One is called crack deflections. You can also have zone shielding, different types of. I cannot discuss all of them in the lecture today. You can have a like transformation toughening, which is known as 2A, 2B is another thing, micro crack toughening. You can generate, instead of one crack, you can generate large number of micro cracks. You can also have void formations. Then you can have a contact shielding, like a crack can be breached, fiber breaching is possible, cracks sliding interference possible, plasticity induced crack closure is possible. Okay, so I will not be able to discuss this part at all, because this is something has to do with the composites. Some part I will discuss about that, but our major discussion will be on transformation toughening. So, question is this now, how do you basically deflect the cracks? If a particle of a second pressure presents, the large difference of elastic modulus can attract or repel the cracks. That is obvious. If a particular phase inside it and there is a huge difference of the elastic modulus or moduli between the matrix and the particles, then we can actually allow the cracks to come or go away from the particle depending on the relative values of the elastic modulus. It has seen that distinguish between a crack bowing, some authors have shown distinguish between crack bowing and crack deflection. Bowing means just bow down. We will see now in picture. Technically, former is toughening from the deflection in the plane of the crack, later is the reflection out of the plane. But in either case, whether it is a crack bows out or it is a deflects, it gives you some kind of a toughening. So, that is why laminates and other things are made. If you have seen that we use laminates on the doors, panels, the basic idea is to create tougher material. So, crack deflection example is this. This is taken from American Ceramic Society, Shaw and Green 1993 paper on silicon carbide based materials. You can see that there are particles like these inside, and the crack actually goes through a treacherous path. It is bending and moving like this. So, when it goes through that, then that means what? The cracks requires more energy to propagate. Our actually system has to be, we have to provide more energy to the system to do that. That means we can load the material higher, or we can actually increase the cycles which material can understand in a typical fatigue test. So, that is the basically one of the particular way of increasing the toughness. This is a very concern. But these are all what is called, these are all done normally, but what is not done, which is typical of transformation toughening, is this one. Okay. If we can induce transformation and do that. So, just before I go to the next lecture, let me just tell you that zirconium oxides has 3 phases, as I told you, cubic, tetragonal and monoclinic. As you see here, this is the zirconium oxide temperature, pure zirconium. So, at about 1240 is basically below 1240 basically monoclinic, then the cubic phase, sorry, tetragonal phase exists, and then finally at very high temperature cubic phase exists. But if you add certain kind of a second phase, like if you add here magnesium, you can actually stabilize the cubic phase. Okay. So, as you see, our cubic phase is stabilized to a temperature of 1400 degrees Celsius temperature. You can clearly see that. Even the cubic phase tetragonal phase is also stabilized at lower concentrations of magnesia, and obviously you cannot get rid of monoclinic phase even at low temperatures. So, that is very clearly shown on the zirconium rich part of the phase diagram. Okay, cubic plus tetragonal and this monoclinic exists, monoclinic plus magnesium oxides. And let us not bother about these dotted lines, these are actually metastable extension of that. Now, lower temperature, and so that means what? Lower the temperature, heat treatment to nucleate small particles of the T phase. That means we can actually first stabilize the cubic phase at high temperature, then cool it down and stabilize these tetragonal phases. Okay. So, very simply I will tell you the idea, then we will discuss in detail. So, if I have a cubic phase at high temperature and I cool it down at about intermediate temperature, something around 1500 degrees Celsius temperature, this will nucleate the term of the tetragonal phase, because this phase field is cubic phase tetragonal, and this tetragonal phase which is shown like a green rods, and if you cool it down, this tetragonal phase will transform to monoclinic. And as you know, tetragonal to monoclinic transformations has a volume change of plus 4.7%, and this volume change, and the volume will increase, will lead to compressive stress development. Okay, that is the basically idea. So, therefore, if you develop a compressive stress around a crack tip, then what will happen? Then it will increase the toughness of the material. Okay, let me stop this lecture here, and we will come back to the next lecture and discuss what is the exact role of these stabilized phases in increasing the toughness of zirconium oxide.